Well, good afternoon. I'm Adam Cuspa, president of the Welch Foundation, and it's my honor to introduce this year's keynote speaker, a citizen scientist who's probably very familiar to many of you, Professor Stephen Chu. Dr. Chu is the William Kenan Professor of Physics, Molecular and Cellular Physiology, and of Energy Science and Engineering at Stanford University. Following a stellar academic career at Stanford University, the University of California at Berkeley, and as director of the Lawrence Berkeley National Laboratory, he served for 4 years as the U.S. Secretary of Energy under President Obama. There he began several initiatives, quite forward-thinking with respect to the energy transition, initiating the ARPA-E, Advanced Research Projects in Energy, the Energy Innovation Hubs, and the Clean Energy Ministerial Meetings. His lab's currently active in a number of areas I'm sure you're aware, including biophysics, molecular cellular physiology, nanoparticle synthesis, and medical imaging. And of course, Dr. Chu has received many awards in his illustrious career, including sharing the 1997 Nobel Prize in Physics for laser cooling and optical trapping of atoms. He's here to speak about materials as an enabling technology in getting us to net greenhouse gas emissions. Please welcome Professor Chu.
You need to. Okay, thank you. While I get a plug, and plug me in. First, it's a great pleasure to be here. Today, I think the last time I spoke at Welch, it was a virtual meeting, and in person is decidedly much better. So in this talk, I was glad to hear that a bunch of the earlier speakers talked a little bit about, or a lot about, what I want to talk about, which means I can shift a little or maybe go faster. So let me just begin. But before I begin, I want to do something that it's not really connected with energy and climate, but we are doing some things using materials as new probes for biology and biomedicine. And one of the things we did before was we made some photo-switchable photoacoustic probes. That means photoacoustic imaging is you shine some light onto a tissue, people, and you create sound waves, and then you use acoustics to actually create the image. So the little burst of sound is then imaged by acoustic imaging. And we developed a method inspired by the photo-switchable probes that give you super resolution. And this method enabled us to make our probes photo-switchable. And in this paper, we showed that we could have a sensitivity of about 10 to the 4 cells using photoacoustics. And we're now submitting a proposal where we think we can go from 10 to the 4 cells to a single cell with photoacoustics with a variety of tricks. Now, the ability to even see a few cells with photoacoustics means you can detect microtumors, which I am told the doctors are not really interested in because most of the body kills the microtumors. Another thing is we developed some nanoprobes. These are rare nanoprobes. We learned how to make them significantly better, orders of magnitude better than what was published before. And we use these probes, 5 million counts a second, to track vesicles and live neurons for tens of minutes without cell damage. And we got 4 nanometer, 1 millisecond resolution. We're building up an apparatus now to give us to 3 angstrom, 0.3 nanometer, 20 microsecond spatial resolution in live cells. Okay, so, but maybe you'll invite me next time for that. So there are some unintended consequences of the industrial and agricultural revolutions. These are these greenhouse gas emissions that you're well familiar with. And the point here is we're going to need another industrial and agricultural revolution. But I want to go and spend a little time on history for this reason. Those who cannot remember the past are condemned to repeat it. But I like this cartoon much better. This fortune teller is saying, you will make the same foolish mistakes you have made before, not only once, but many, many times again. Okay, so pay attention to history. So in the development of civilization, you look at the beginning of agriculture. The beginning of agriculture meant that you no longer were hunter and gatherers. You could actually stay there. You can create more wealth. You can then actually support kings and physicists. And so with the first agricultural revolution, things percolate along. And according to this Robert Vogel, who won a Nobel Prize for economics, it was really the second agricultural revolution that turned things on. Surprisingly, the first agricultural revolution were technology developments, domestication of wheat, rice, cattle, yeast, fermentation, things like that. The second agricultural revolution was a revolution in policy. It meant you can do enclosures, so you can fence the land, and instead of everyone getting to use the land, which means it's overgrazed, you can actually have productive farms, and also the development of tariffs, transportation, things like that. What was the third agricultural revolution? The ability to make nitrogen-based fertilizers from ammonia, from air. And that was awarded 2 Nobel Prizes, first to Fritz Haber in 1918 for the synthesis of ammonia, and then to Carl Bosch for the Haber-Bosch process, which he did with Fritz Haber before Haber's Nobel Prize. But they had to think of a reason to give it to him, so they said it was for high temperature, high pressure, catalysis, but that was used in the first process. Another part of the agricultural revolution is breeding plants. Norman Borlaug started this in the 50s and 40s, actually, with the breeding of dwarf strains of wheat, and other people followed for all the major grains. And so these 3 Nobel Prizes led to an amazing thing. When you go from 1960 to 2000, the population of the world went from 3 billion to 7.4 billion. The land put under cereal production did not increase. And the productivity went up 3.5-fold. That's around the world. In countries like the United States, maybe 5 or 6-fold. And so that was a very big deal. Now, let me remind you a little bit of history. Here's a little quiz. I'm a professor. Can you tell the native corn from the corn we eat today? The point is, we've bred the things we've eaten so they're unrecognizable. In terms of the livestock we eat, if the full circle is the lifetime of, let's say, beef or pigs or chickens, that little red segment is the time in which they're slaughtered. So for beef, it's 18 to 24 months, pigs 22 to 26 weeks. This is kind of astounding because after about 24 weeks, the average American pig weighs 280 pounds. This is fast growth. And so they've been optimized to grow very, very rapidly, a very small fraction of the nitrogen cycles. Turkeys are bred to be very breast heavy. They're slaughtered typically 3.5 months after birth. But for some of these, they're so breast heavy they can't mate. So these are not as recognizable, let's say, as a wild turkey. I don't know how old these wild turkeys are. I can tell you how old this wild turkey is. Okay, so moving right along. If you consider the greenhouse gas emissions from beef and dairy cattle and compare that to the greenhouse gas emissions of countries around the world, this happens to go to 2020. China is leading the pack, followed by the United States and EU 28. But if beef and dairy cattle were a country, they would have more greenhouse gas emissions than the United States, which is quite a lot. I should also say that if you take all the biomass of humans and the animals we eat and put it on one side of the scale, and all the other mammals in the world and put it on the other side of the scale, 96% of biomass is us and the things we eat. And the things we eat are cycled every year, year and a half. So this, if you want to talk about geoengineering, agriculture is geoengineering. But there are some other things in addition to, let's say, methane emissions from livestock, and that is nitrous oxide is a real issue. These are the significant greenhouse gases, methane, CO2, and nitrous oxide. Nitrous oxide is about 300 times worse than CO2 in terms of a greenhouse gas. So even though it's less than 0.3 parts per billion, well, it's 0.35 parts per billion, it's growing very rapidly, and it's growing very rapidly because of the increased use of fertilizer around the world. In a world of 3 to 7 to 8 billion people, we're more dependent on fertilizer. And fertilizer is 75%, 74% of greenhouse gas emissions. If you include that with food waste, it's even more. So there's a dilemma. How do you get rid of fertilizer and yet feed 8 billion going to 11 billion people? So we don't really know. There is a possibility. Synthetic biology may offer some hope. And by that I mean that one could engineer microbes, so you plant them with grains. This has already been done with corn. And so the microbes enter into a symbiotic relationship with the plant. They're right at the rhizome, at the boundary of the roots and the soil, and the plant says, "Feed me," and the microbes feed them. And so with the microbes now, we got rid of half the fertilizer, but you need to get rid of all the fertilizer, and it's got to be done not only for corn, but for wheat, rice, you name it. And so that's one of the issues that we face. The development time for those microbes was too long. It was roughly 7 to 8 years. The hang-up is you can only manipulate one gene and one promoter at a time, and you may need dozens. The good news is help is on the way. We're figuring out in my lab that we can put in 10 genes at a time, very parallel with high cell efficiency. And so if this is successful, then maybe there would be a big boost to synthetic biology. But let's return back to the Industrial Revolution. And we're all aware of images, for example, this one, where you see a horse-drawn carriage, and it's being replaced by a steam engine. And this transition marked the transition from using horses as power to horsepower. One of my favorite paintings was a Turner, where you have a picture of a steamship towing an iconic sailing vessel that had a glorious military past somewhere in London, and the steamship was towing it to be broken up for scrap. And so you have a setting sun because this is the setting of the sailing era. Okay. What does this have to do with materials? Well, it turned out that materials was a foundation, if not the foundation, for the Industrial Revolution. And it was Henry Bessemer's ability to make steel, which actually led to both iron and steel and the Industrial Revolution. Ironically, and maybe not ironically, but his invention of the Bessemer process was to solve a military problem. There was a Crimean War, not this one, but the one before. And they had cast iron cannons, and their new shells were better explosives, and so the cast iron cannons would break. So he had to develop a stronger material that could do this, and that led to the Bessemer steel production methods. You already heard of the transistor and how crucial the materials development was for the transistor. But there's a long cry from the original point contact transistor of Bardini and Bertin. Shockley's name was not on the transistor patent. And the transistor junction transistor, which is why Shockley did share the Nobel Prize, because he laid the basic physics of p-n junctions that led to the junction transistor. It was a long cry from this stuff to what we have today. And there were two breakthroughs. One breakthrough was by Bill Fan at Bell Labs, that he introduced an idea called zone refining, where you can get very, very pure germanium, and another by Thiel, who actually took a single crystal, imitating a method by Cherkassky that Cherkassky did in 1915 to make single crystal metals. They put a single crystal of germanium in a vat and drew it out slowly to make single crystal germanium, followed by single crystal silicon. So these things were really the key. When I was a young scientist at Bell Labs, my first year there, I was in this office, and I sort of noticed this old guy. He would walk in there, and he'd kind of putter around for a couple hours. He'd barely say hello. We'd nod at each other, and he'd walk away. So finally I asked my department head, says, "Who's this guy?" And he said, "You don't know who that guy is?" "No, who's it?" "He's Bill Fan." "Oh, what did he do?" He says, "He gave us pure germanium. He can do whatever he wants to do at Bell Labs now." And so my department had finished it. It says, "You remind me of these two cavemen. They're looking by, these young cavemen, they're looking by this old doddering guy who looks like, who's he?" "You don't know who he is?" "No, he invented the wheel." "Yeah, but what did he do lately?" Anyway, optical communications, fiber optics. I was at Bell Labs when these things were being done by Corning and Bell Laboratories to get really low, high purity, low loss optical fibers. And without that, optical fibers would be nothing. So now they're about 0.14 dB per kilometer. It's amazing stuff. The point is, the basis of all these revolutions were materials. Okay, let me talk about other things that we have to face. We're going to go to electricity distribution. We need clean energy to make steel, cement, chemicals, plastics. We need to decarbonize. In addition to having clean energy, we need to decarbonize those areas. And so let me talk about solar photovoltaics. I just want to mention one thing that Gretzel already said, but I want to drive this home. There's great promise for perovskites and perovskites with silicon. And a large part of the Department of Energy roadmap to get to halve the cost of solar today is that we are going from 20-year solar cells to 30-year solar cells. And that is crucial. And so the big challenge of perovskites, as already pointed out, is that if they're going to come close, they better last 20 or 30 years. Having high efficiency for 10 years or 20 years doesn't count. Okay? And balance of systems, BOS, is roughly proportional to the weight of the solar cells, and we don't have anything to replace glass yet. So you think of plastics and polymers, they're more expensive, or they degrade in UV, or both. They're actually more expensive and they degrade in UV. So this is something to think about. How do we get beyond glass? Electricity transmission and distribution. Well, if you look at, for example, the map of the world in terms of solar capacity, where you see these dark reds as being fantastic, and where you see these light colors like light green and bluish as being terrible. For example, here's Germany, which has about as good solar as Seattle, which is cloudy most of the time. You want to think of generating solar power over here. So let's zoom in on that section of northern Africa. Fantastic power. And so one is now beginning to dream of having transmission lines, high voltage transmission lines, that could take this power and get it to Europe, which has much less solar energy. Also, you see here the transmission lines in operation, under construction, being planned. Many of these transmission lines go underwater. And so the issue here is the limitation of power in transmission lines underwater is the dielectric strength. And so one has to make better dielectrics. Let me give you a sense of what these transmission lines look like. This is a transmission line, a 1.1 million volt transmission line in China. These things here are people. That's the electrical standoff. This transmission line goes 2,000 miles and loses about 5% of the power. It's very, very efficient. It transmits 12 gigawatts of power. All right? The undersea cables only can transmit roughly 500 kilovolts, but since the resistance goes as V squared over R, doubling this really means you can actually have 4 times more power. So to actually make better dielectric materials is a very big deal for distribution transmission lines. To give you another sense of the scale of these very high voltage transmission lines, that's a transformer. Those little things down there are people. All right, so let's talk about wire in transmission lines. The highest voltage, highest power transmission lines aren't insulated, they're just bare aluminum. But aluminum is not that strong, so they put a steel core inside the aluminum so that these wires can remain suspended. If you annealed the aluminum to make it better conductor, then it's actually its tensile strength is weakened. So it's that polycrystalline stuff that actually keeps it some tensile strength. And so now people are beginning to look at annealed aluminum and inside a carbon conductor. And so with that, I thank Matteo Pasquale, who promised me he would be here, but if he's, there you are. So he's done some really great stuff over the last decade. This is adapted from one of his slides. And this slide tells you about what are the materials we use today in large quantities. Besides oil, coal, and natural gas, there are things like concrete, asphalt, cement, glass, and brick. These are very inexpensive things typically used in structures. Then we have these metals, steel, aluminum alloys, copper, and then zinc. And all this stuff has large carbon footprints. And so the question is, can there be materials around the corner that can start to replace some of these? And so what Matteo has been working on is if you take methane, natural gas that you get out of the ground, and if you can turn methane into carbon fibers inexpensively, cheaply, you begin to turn this corner. And so here is another slide adapted from his work, where you have electrical conductivity on the x-axis, the strength on the y-axis. These are the steels. That's the steel core that supports the transmission lines. Over here, this is a log graph, and so roughly an order of magnitude higher, you have the carbon fibers. And and on the right-hand side, when you're looking at the specific electrical conductivity, this is steel over here, and on the right and over here is carbon fibers. So not only is the carbon fiber much stronger, it's actually a much better conductor. In addition to that, the learning curve is pretty good. This is again from Pasquale's work from 2004 to 2020, and it's improving by about 26%, 23% per year. And so we don't expect it to get to superconductivity, but it's already in a place where cost is everything, and you want to begin to substitute these carbon fibers from steel. All right, what's some of the other frontiers? Well, there's wideband semiconductor electronics. We started with germanium because we learned how to make germanium ultra pure very quickly at Bell Labs. But then because of a wire bandgap silicon, one quickly realized you can go to silicon if you can make silicon pure. And the zone refining process was not good enough for that. It was the Charkovsky process that finally made silicon pure enough. But then there are these wider bandgap materials, silicon carbide, gallium nitride, and zinc oxide. So when I was Secretary of Energy, we decided to put a lot of money into materials development of gallium nitride, silicon carbide, and other materials because the people that make electrical components won't do any research on materials development. And this was the hang-up. And so we started doing that. Just to remind you, the blue LED Nobel Prize, it was because we learned how to make very good gallium nitride, first with MBE and then with vapor phase deposition. In power electronics, this is the stuff that's going to do these transmission lines. If you go to wide bandgap, you can actually reduce the electrical losses by about 90%. You go to higher frequencies, which means you need less iron and these high frequency up conversion from AC to DC and DC back to AC. And finally, it's good and everything. I cannot stress how important improving power electronics is in terms of energy efficiency. Right now, 30% of the electrical use goes through power electronics, and it's estimated by 2040, maybe 80% will go through power electronics. I should say that EVs, the first standard of voltage systems in electrical vehicles is at 400 volts. They're going to 800 volts. And then soon, maybe they're going to 800 volts because of V squared over R. The car has less copper. It weighs less. It costs less. And then to 1200 volts. Because of power electronics. As the cost of power electronics at high voltage comes down, you can begin to do these things. This is an example of something we funded our Secretary of Energy using silicon carbide. One was able to make a 1 megawatt transistor that could be used for high frequency switching. Anyway, so what else do you need in electronics? Well, the energy used in information and communications technologies is a lot. If you look at globally, we're not talking about just in the United States where, you know, one's kids are playing video games for 4 hours a day, but average globally, it's estimated that 5 to 8% of all electricity is now used in data processing or in communications. Shockingly, blockchain technology uses half the energy of all data centers in 2021. That's this crypto stuff. As far as I'm concerned, that should be outlawed because it's only used to launder money anyway. That's not its only use. You can also defraud people. The Internet of Things, which everybody's so very happy about, there's an estimate from a British study that says a 3-fold increase in energy consumption in the next 5 years. And then machine learning is really crazy because the machine learning, the NVIDIA chips that are the heart of the machine learning chips are power hogs, and machine learning is going crazy. And so we really don't know what this is going to be, but it's going to be a lot. And so much more efficient electronics is a must. I should also say that because of the high replacement cycle of electronics and computers and everything, there's an embodied energy of making it, assembling it, and then disposing it, and that's 20 to 30% of this energy. So what's happening? How do you want to break out of Moore's law? There's some crazy stuff. The first really successful transistors large scales with the so-called CMOS technology is that you have a gate and you can, by putting a voltage on the gate, you can adjust the current from the source to the drain. What was developed after that is called a FinFET technology. So it's an FET, but now it goes up laterally across like this. And so in this technology, you can make everything smaller because the voltage now surrounds these sources and drains. And now people are going to nanoribbons. By nanoribbons, I really mean 2D materials, graphene, separated by 2D insulators like hexagonal boron nitride. And people are actually trying to learn how to make this lithographically with a few nanometer design rule. It's crazy. And why you do this? Because of energy consumption. Finally, there's a new kid on the block. Whether CMOS will ever be replaced, I don't know. It's like silicon in photovoltaics, but occasionally something could happen. And there's a new material called ferroelectrics, and perovskites, again, is the leading player in this new material that one thinks you, in principle, use it for memory and logic. Ferroelectrics means for memory, for example, so DRAM, it's a charge on a capacitor, and the charge leaks away, and so you've got to recharge it to make sure you didn't lose your memory. So it's kind of like reminding the transistor or the memory, every, I don't know, 10 times a second or something. Remember, I'm still here, or you should remember this. Ferroelectrics is like a spin flip in a magnet. You flip it, and then you don't need it anymore. And so the ability to reduce power and also into nanotechnology is huge. Two of my friends, one is Ramesh, who I recruited to head the Sunshot program in the Department of Energy when I was secretary. He was a professor at Berkeley, now lured over to Rice University to be their head of research. He founded a company called Kepler, which is trying to make memory and logic gates from ferroelectrics. And they've coupled with Om Nalamasu. I did it wrong, but anyway, I just know him as known. He's the Senior Vice President and Chief Technology Officer of Applied Materials. So full disclosure, I'm an advisor to Kepler and to Applied Materials. But I got these two guys together, and it was a materials problem. And getting the longevity they need was due to Applied Materials' expertise in controlling at an atomic level interfaces. They need only a couple orders of magnitude. Before, they were many orders of magnitude away from longevity, but getting much better. All right, batteries. Another thing of good use. Here's a picture of my favorite battery. Let me explain how it works. When the wind blows, you do the energy-intensive thing, namely pumping water underground for irrigation. And so it turns out that pump storage, lifting water up a hill, is 95% of all electrical storage. In 2021, these are the countries that led in pumped hydropower storage. It's led by China on the top, followed by the United States and Japan. The United States has recognized that pump storage still could be very useful, and so it's it's permitted an additional 19 gigawatts of pumped storage power. If all those projects are built, it goes up by nearly 1.9. So what is China doing? Well, they're building pump storage over here, and it goes off the slide by a lot. They have 34 gigawatts of pump storage, and they want 270. So they want more than double the rest of the world combined, because they realize it's a really good battery. All right, just to let you know that engineering scale is a little different. This is pictures of a hydroturbine pump on the upper left-hand side, a generator on the right-hand side, and those are the people. Nevertheless, this is the current battery we have. We are looking at different ways of storing energy. A lot of focus now is both on hydrogen as a energy storage means. So it's chemical storage without the overhead of the other stuff in a battery. But also, if you could make a synthetic methane from capturing carbon out of the atmosphere, that too could be a very green source. In all of these technologies, whether it's electrolysis or green methane or better ammonia production, it all depends on catalysts that are earth abundant. So it's, again, a materials problem. Now, in the end, what do we want? We want to take carbon dioxide and water, and we want to use clean energy with whatever means to begin making hydrogen and then CO, but don't stop there. You want to make economically viable hydrocarbon fuels, because hydrocarbons pack a lot of energy density. The reason you want this is because if you can store energy in liquid form, it ships very well. And by ships very well, I mean the following. If you think of a supertanker and it moves crude oil halfway around the world, let's say from the Middle East to Japan, and ask how much does it add to the price of a gallon of gasoline, and the answer is about 2 cents. Okay? So if you can get liquid hydrocarbon energy starting with ammonia or methanol, green methanol, or anything like that, and put it on a tanker, this is the intercontinental transmission line of the world. So again, how do you get that? It's all about, energy is all about money, and so this is the goal. Well, the batteries, these are the chemical batteries used in electric vehicles. Here I plot energy per unit weight on the x-axis, energy per unit volume on the y-axis. Energy per unit volume is the crucial figure of merit for cell phones, both volume and weight for EVs, weight for anything that goes in the air like a drone. So this is where the Tesla S1 battery is today, and this is where it's going in the next 10 years. It's likely to double. I know this because I'm on the board of a battery company, and we're shipping out samples like these. So shipping out samples and getting them into cars is at least 7 or 8 years. Just the safety issue of cars is that. The other good news about batteries is that this is the learning curve. So on the x-axis is the amount of batteries that have been shipped out, have been produced, and it's a logarithmic scale. It's powers of 10. And on the y-axis is cost, also on a logarithmic scale. And so whenever you see something like this, you're getting an established technology and you're racing down a learning curve. This learning curve is pretty good. Starting year 2000, lithium-ion batteries were $2,000 a kilowatt hour, not practical for much. By 2020, dropped to $100 a kilowatt hour manufacturing costs. By 2030, $50. And so the question is, what will stop the learning curve? And one of the things that could stop the learning curve is there could be a resource constraint. As an example, we're already switching from alloys in the battery cathode material of nickel, cobalt, and manganese to iron phosphate because nickel and cobalt are limited. and it's becoming too expensive, even though the iron phosphate has less energy density. And so what is happening? So what is happening is you want more ways of sourcing lithium. And so this is Chong Lu, who's an assistant professor at the University of Chicago. When she was a postdoc at Stanford, she worked with Yihui and myself to develop a way of extracting lithium from seawater. She's continued that work at the University of Chicago. And the bottom line is that when you start with seawater, where the ratio of lithium to sodium is 1 in 20,000 molecules, or atoms rather, or ions, with one pass through iron phosphate and back out, with some tricks, she can get the ratio to 8 lithiums to 1 sodium. So if this is practical, then voila, you've just increased the source of lithium by 10,000-fold. And anyone who has access to the ocean can have this. So we'll wait and see. So maybe lithium is taken care of, but as I said before, nickel, manganese, cobalt, not so good. Iron phosphate, lots of iron phosphate, not a problem, but lower energy density. Theoretically, if you had a sulfur cathode, you could increase the energy density about tenfold. A lithium metal anode sulfur cathode has an energy density could be 10 times higher than today's EV cars, batteries. So what's the problem? Well, when you plate, if you charge lithium at any reasonable rate, little imperfections start, and these little imperfections concentrate the electric field over here, and then dendrites form, and that they snake over and short out the battery. And so one of the strategies could be if you had a really tough material that could supplement the solid electrolyte interface layer that forms naturally, that has very high Young's modulus, but lets lithium ions pass very quickly, then these dendrites could not form. And so we've been playing with this, and what we found is that if you take hexagonal boron nitride and radiation damage it to make little holes, you can get something that lasts quite a long period of time. And so we made a little coin cell and found that the battery remains stable, absolutely flat stable, until the chemistry of the electrolyte and the lithium drain the electrolyte and the battery dries up. So this is very good news. But again, it's a materials problem because our original supplier forgot how to make this stuff, and the precursors became less pure, and so all of a sudden we're in the materials growth business again, like with nanotechnology. So we are trying to now make very large areas, it's got to be meters wide and cheap, of hexagonal boron nitride. But it's of great promise because it does pass lithium ions really easily, and it stops degradation. The same technology means that you can think of aqueous batteries. These are, okay, lithium will be good for EVs, but when you go to utility scale, you need another 3 orders of magnitude increase in the amount of batteries for utility scale. And all of a sudden, lithium, there's not enough lithium, and it has to be an aqueous solution. It can't use the electrolytes we use today because those things can still catch fire. And having acres and acres of something that catch fire is not good. So we're thinking earth-abundant metals in aqueous solution, but the water does electrochemistry on this stuff, and that limits the voltage operating range to a volt. And so what we're about to examine is whether our radiation-damaged hexagonal boron nitride actually, it should strip the hydration shell around the ions. So then the ions just simply go through the stuff, the water's left behind, and it goes into a metal. And that would be very exciting. But that's research. Having said all this, and having talked about energy storage, I need to tell you that we still need things that we can turn on. And by things that we can turn on, I really mean natural gas or nuclear power. I'm assuming 10 or 20 years from 30 years from today, coal will be waning. So let me make a quick plug for nuclear. This is a 50 megawatt NuScale fission reactor. That's the whole thing. The coolant, the reservoir, everything. It can fit on a flatbed truck. There's a new economics that's available now because, first of all, you can make these things, hopefully, that can go for 5, 10, even longer years without refueling. They're made in a factory. And the economics are that you use this 5% at a time when batteries or hydro run out. And the rest of the time, you can use it to make hydrogen or desalinization. You still got to use the nuclear power plant 100% at a time, but we already know that gas generators used only 5% of the time are profitable, because in that 5% of the time, you get to charge 100 times more for electricity because you're facing a blackout. So that means that this could be viable, but there are materials problems. There's stress corrosion, there's radiation-assisted corrosion, there's all sorts of things. And on the positive side, some of the new designs are calling for very innovative ways of doing nuclear fuel. Of course, people are scared of nuclear power, but they should think a little bit more deeply. If you look at the amount of deaths arising from the production of electricity, brown coal and coal lead the pack, followed by oil, biomass, and where's nuclear, including Chernobyl? It's down here. It's a little bit safer than wind. It's more than 100 times safer than burning wood pellets because of the particulate matter in the wood pellets. And so the other good technologies coming along is you can now think of boreholes 1 meter wide going down very deeply to access geological strata that can store the spent fuel, but you don't need people, and the cost, we hope, comes down as it does the difference between humans in flight, space flight, versus unmanned flight. So what about fusion? Well, commercial fusion will not happen unless you solve the neutron damage problem, period, end of story. And right now, the design for any demonstration plant after ITER would be a sacrificial layer of material that crumbles in about 5 or 6 years. So it's crumbling, it's radioactive, so you're going to go in there, break vacuum, go in there, take it out, put in a new liner in there. This is all precision stuff, and you have to go back in there. This is not something you do in a week, and it is radioactive. So that's an issue. Inertial fusion has other issues. And so when I think of the time for commercial fusion, optimistically, it could be 25 years. But the person who made the ITER fusion work, a physicist friend of mine, he agrees with me. The more likely time scale is never for commercial fusion. Fusion, yes, the experiment in ITER will work. I'm convinced of it. But the neutron damage is unsolved. Need for high temperature materials. It's all driven by Carnot efficiencies if it has anything to do with heat. You may not know this, but the turbines on the airplanes you fly on are operating at temperatures. The combustion engine in that turbine is operating at 1600 degrees C. The softening temperature of the turbine blades is 1100 degrees C. So what are they doing? They're actually letting air cooled by the fuel to go into these turbines to set up laminar flow so that there's a thin layer of air that insulates the blades from the high temperatures. And so for that reason, they're just going up and up in temperature, and the engines are 50% going to twofold more efficient than they were 30 years ago. But we also need high temperature for a lot of things: solar storage, thermal storage. Thermal storage costs more than photovoltaic, but it has the advantage that it stores heat energy. And so these are some of the projects. UAE and Morocco they're just completing those. US Power had been completed a couple of years ago. So all limited by high temperature materials. Innovative ways of getting heat stored in the form of batteries. This is an idea of Bob Laughlin, where they're using a turbine to pump heat, as you would a refrigerator, from low temperature to high temperature, and from high temperature to low temperature. And I don't have time to explain it, but just say that the turbine is 100% efficient, and the heat transfer is 100% efficient. The efficiency is 1. Now, he thinks that he can get to 70 or 80%, but he's stretching the limit of what you can do in terms of the temperature difference of the reservoir. And so the temperatures he's assuming are the highest you can get with commercially available mass-produced materials. So going by 50 degrees is a big deal, even 50 degrees, let alone 100 degrees. Finally, carbon capture. It's going to have to be necessary, but we're going to go over 450 parts per million within a decade or two. We'll go over 500, 550 parts per million by the end of this century. And so, we have to look at carbon capture. And materials, again, is a crucial element in this. In one version of carbon capture, most carbon captures use these amine molecules appended to something on a nanoparticle, microparticle, or on a polymer matrix. This carbon capture company, Svante, uses amines appended onto a matrix. But the nice thing about this is, again, full disclosure, I'm on the board of this company, but this is maybe the first commercial application of metal organic framework particles. BASF is beginning to manufacture them for us because they're interested enough to actually invest some of their time and money as well. Okay, so wrapping up, despite the fact I'm working on carbon capture, I think the best carbon capture is the one nature provides. If you look at crops we grow, they're capturing anywhere from 10 to 18 gigatons a year. Virtually all of that gets recycled as the plants are burned or rot away. But you compare the 10 to 20, 18 gigatons a year to total human emissions of 52 gigatons a year, of which 40 is carbon dioxide. So photosynthesis is really good, and so the issue is, can you actually take all the crop residue that we don't eat and don't plow back into the ground, which is most of it, can you use that carbon, compress it cheaply, and make sure that it doesn't turn into CO2 or methane? And so how do you do that? Well, you do that by one of two ways. Either sterilizing it with some means, or Eli Lubonovich has now formed a new company where he said, you know what, if you just dry it out below a certain amount, then wrap it into a non-degradable baggie, big plastic bag, bacteria won't grow. How much mass are we talking about? Well, it's actually to sequester a couple of gigatons a year, we're talking no more than landfill that we use in cities. But this is going to be out in farms. So again, oh, by the way, put to scale on things, we now sequester experimentally about 50 million tons. We need to sequester 10 billion tons to be 1/5 of the carbon emission from agriculture or from other things that we don't have solutions to yet. Okay, finally, let me introduce a really novel material. This is good because it sequesters carbon, and it's called wood. So think about this. You grow forest, you use it for lumber, okay? But can you build 5 and 10, in this case 20-story tall buildings using wood as the structural member? And the answer is you can. But we still build even 5-story buildings out of steel and concrete. So a carbon price that will discourage steel and concrete with high carbon content and one that rewards sequestering wood would go a long way to changing this. And so with that, I just wanted to, this is, it can be very good. This is the oat mill company, Oatly, and they took an old building and they left the steel girders, and on that they put in wood structures. Okay, so this sequesters carbon, and it can do a lot. I'm going to skip that and just remind you, again, one of my favorite photos was this picture taken by Apollo 8, the first to orbit the moon in preparation for the lunar landing. And the astronaut who took this picture said, "We came all this way to explore the moon. The most important thing is we've discovered the Earth." So the lesson is, moon is not a good place to live. There's no atmosphere, there's no water. Well, there might be some water in the poles, but there's no shielding of cosmic rays, so you'll die of cancer. And there's lovely Earth and nowhere to go. Thank you. Should I leave? Okay, I've been told I have to leave. Should leave.